Okay, vertical kinematics, free fall, anything in free fall. So what are things that are in free fall? All right, an object is in free fall if it's falling and almost the only influence is actually no air resistance. So if you have a lot of air resistance, like our parachute is here in the middle of our picture, that is not considered free fall. If you are a feather in our regular atmosphere, as it falls down, it doesn't fall straight down, it floats down. Okay, so if you get that going on, it's not considered free fall. Free fall has to be something that has little enough air resistance that it, for the most part, falls straight down at a normal acceleration, getting close to negative 9.8 meters per second squared for our acceleration. So in class we do some demos where if you take a sheet of paper, it will float down, but if you crumple that sheet of paper up, it will fall straight down at the same speed as, say, a book. Okay, and then you can show, once you've shown that, you've shown that the book goes straight down, you can put the paper on top of the book, and because the book breaks the air resistance, breaks the air, then the sheet of paper falls just in line with the textbook. We won't talk about anything that would also help keep it there. Just the idea that with air being broken by the book, the weight of the book, then the object will fall down. So most objects fall down at pretty close to the same amount of acceleration. There is, for every object, a little bit of air resistance. So if you have things of equal weight with a little bit different volume, the thing that's a little bit smaller might fall a little bit faster. If you have something that's larger and much more heavy, it might fall faster as something that has the, close to the same size. But it's not going to be something you can notice too much with your naked eye. Now, if we can take air resistance out of the equation, now you can Google hammer and feather on the moon, and you will see Apollo 15, where the astronauts took a hammer and a feather and dropped them at the moon, where there's basically no atmosphere. It doesn't have enough gravitational attraction to create an atmosphere there and hold things in. So they fall just along with each other. Also, you can look at Mythbusters, and they've done that. They went to one of the NASA centers in Alabama, and they dropped the hammer and the nail in a regular atmosphere inside a container. Then they sucked all the air out of there and created a new vacuum, dropped them, and you saw the hammer and the feather fall at the same rate. So free fall occurs when you don't have much air resistance at all. Okay, so 3 scenarios. When you drop an object, if you drop an object, then your change in your height is going to be negative. Let's say this guy was at 2 meters. It's going to fall down here to 0 meters. That means the change in y equals negative 2 meters because he lost. He went from 2 to 0, so he lost 2. So it's going to be negative 2 meters. Since you dropped it, your Vy, or Vi, your initial velocity, is 0. Now the same thing actually happens if you throw it with an initial velocity equaling 10. The formula will be the same. What we'll use is the formula delta x, or delta y, equals Vf squared minus Vi squared over 2 times the acceleration due to gravity. So that's the equation we'll use. We're just going to keep this stuff pretty simple and solve for this using one thing. We're going to have our Vi being 0.
Mr. Spana, can you report to the counseling office? Mr. Spana?
Okay, so obviously school's still here. All right. Now, we're not going to do any math with this scenario, but here's a good scenario to remember. If you throw a ball up, it goes up, reaches the top peak, and then falls back down. So your initial velocity will be equal to the same velocity on the other side. When it hits your hand, it will hit going downward. Downward is a negative direction, so it shows up as the negative speed of your original speed. So negative 5 versus positive 5. Your change in your displacement, in your height, is 0, because if you start at 1 meter and you end at 1 meter, it hasn't gone anywhere. That's displacement. We're not going to do any math with this, but it does lead us, as the object goes up to the top and it falls back down, at the very top, we're going to have a Vy or a V final at the top. Let's say the object just stopped right here, just stopped forever. Then, we'd have a Vf up here of 0. That leads us to our next one, which we'll be doing some math with. Find the height Okay? To find how high you can throw something up, when the object goes up, it's going to go up till it's not going up anymore. It's going to instantaneously stop and start falling back down. So for the briefest of moments, you're going to have a velocity of 0 at its highest point. Only at its highest point do we have that brief momentous 0 meters per second. So you take your throwing up, whatever your speed is, that's your initial speed. Your VF being 0 to figure out how high it will go, and you can use the delta x equals VF squared minus VI squared over 2 times A. So we can again use this same equation to figure out how fast it's going, how high it will go. When we drop something, I shouldn't have done this, we don't care, we're going to be told how high we are. What we'll be doing on this one is we'll be solving for VF using VF squared equals VI squared plus 2A delta x. If I was wrong on that one, let's correct that. And what we have to do is we have to take the square root of that answer. Because we're solving for VF squared, we want to solve for VF. We have to take the square root of this answer. And we're going to cause it, because we're going downward, we're going to make that the negative. Remember that 2 squared and negative 2 squared both give us 4. So when you get a square root, it's a positive and a negative. We're going to choose the negative of that square root. All right, so here are all of our kinematic equations we looked at earlier, and we're changing to delta y instead of delta x. The delta y just is talking about the fact that we're working on the y-axis. This is a graphing situation. The x-axis left to right, the y-axis up and down. On our test, since it's a mixed bag of things, we're just going to keep using delta x. So anytime we have displacement or distance, we're going to use delta x. So let's work an example problem and of each type where we're dropping something or we're throwing something up in the air, and then we'll be done. So let's work this problem. We have an object that is dropped from a 15-meter ledge. How fast is it going as it hits the ground? So an object that's dropped means it has an initial velocity of 0. And it's going to fall from 15 meters all the way down to the bottom. So it's going to lose 15 meters. And in all these instances, we're falling only under the influence of gravity, so our acceleration is going to be equal to the negative 9.8 of gravity. How fast means we're looking for VF. So VF is our unknown, VI is 0, acceleration is negative 9.8, and our change in our displacement is going to be negative 15. So our formula is VF squared equals VI squared plus 2 times A times delta x. So 0 plus 2 times negative 9.8 times negative 15. You plug that into your calculator. Let me do that. I'll turn this off and do that. And you do it also, and then come back and check your answer. So pause your recording. All right. So our answer is 294. But we have solved for VF squared, and what we want is VF. So what we have to do is take the square root of the VF and the square root of our answer, and that makes VF 17.15, and VF is in meters per second. But remember, anytime you have a square root, you get a plus or minus to your answer. Since we are falling down as we hit the ground, we want to put a negative in there for our speed. So our final answer is going to be, my final velocity being negative 17.15 meters per second. So it's hard to remember all these negatives, so it just takes repetition and working with things. All right, let's work a problem where we throw something up. Okay, a ball is thrown 24 meters per second into the air. How high does it go up? Okay, how high is our delta x or delta y? Our acceleration going to be negative 9.8. We're looking for delta x. It's thrown with an initial velocity of 24. And we need one more thing. So as an object goes up, it reaches its highest point and then begins to fall down. At that point at the very top, the VF, right up here at the very top, we're going to call that 0. That's our highest point. When we stop going up, we're no longer moving up. When we start to fall down, our VF is 0. So we're going to rearrange that same equation and say delta x equals VF squared minus VI squared over, and put your in parentheses, 2 times the acceleration. So when you plug these in, you get 0 minus 24 squared divided by 2 times negative 9.8. You must put the 2 times negative 9.8 in parentheses like it's showing up here on my paper. If it doesn't look like that in your calculator as you put it in, your answer will be incorrect. So our answer on that is 29.39. Now we solve for delta x, and so our unit is going to be the meter. I don't have to square root this answer because I'm not solving for VF squared. I'm solving for delta x. Delta x is not squared, so there's no square root we have to do. All right, the process is simple. You just have to pay attention. Are we seeing how high it goes up? If we're seeing how high it goes up, the thing that we know is that our VF is 0. If we're asked to solve for something where we drop something and then it falls down, then we have to remember that as long as they give us the height will be a negative, and our VI is usually 0. But I can throw it down and have acceleration take it. It will be worked the exact same way, except instead of 0, we'll put in the velocity that they tell us that they threw it down with. So we're going to work some problems and try and help you get a little bit better at it. So good luck with this stuff, guys.